Hello everyone. The application is a student management system designed to efficiently manage a large dataset of student records. The primary goals of the application are efficient searching, sorted traversal, dynamic updates, performance metrics, user-friendly interface. The application reads data from a CSV file containing detailed student performance records. Each row in the dataset corresponds to the student's record, with fields representing personal details and academic performance across various subjects. The main operations are search by name, delete by name, view all records. So the part A is a discussion. Based on the question, my answer is the time required for the insertion operation in a tree increases when you consider the search operation to ensure that the item being inserted is not already present. Since searching is already part of the insertion logic in a standard application, explicitly adding a preliminary search check doubts the time required for the search step. The overall time complexity for the insertion operation with the explicit existence check remains the big O log n, but the consistent factor increases slightly due to the additional search step. The part B is time consuming. The insert time and the search time between the BSD, AVL, and B-tree. So the analysis in BSD, the insertion operations are relatively fast, but when the tree is unbalanced, the time to look up operation may degrade to linear. If data is inserted sequentially, the tree becomes like the trend list with a poor lookup performance. The AVL tree, the insertion is a little slower because of the need to keep the tree balanced. But since the tree is always balanced, the lookup time is always logarithmically big O log n, so it is very efficient. So the conclusion is, for random access patterns, AVL tree is the optimal choice because it generates that both insertion and lookup operations are maintained and logarithmic time complexity for the large data volumes. If the insertion performance is the main concern and there is no serious imbalance problem in the data, a plain binary search tree can also be the suitable choice, but it's the worst case performance and it's poor. So it's part C, the insertion of AVL and BSD. The AVL insert time rates linearly, reflecting the big O log n complexity. The BSD shows the slightly lower insertion time overall, benefiting from the simple logic, but may suffer from the efficiency is imbalanced case. The AVL tree are better for the application requiring low-turn optimal stability, but BSDs are more efficient for scenarios with fewer updates and low balancing needs. So this is the bar charts and line charts of the AVL, and this is the BSD bar charts and line charts. This is the search time consuming. The AVL tree outperforms the BSD in search efficiency with a constantly lower average time across 100, 500, and 10 and 1000 operations. AVL maintains a balanced structure, keeping search complexity at big O log n, resulting in stable and efficient performance. In contrast, the BSD average time fluctuates, likely due to the imbalanced tree structure, causing higher search cost in certain scenarios. This highlights AVL average in application requiring the frequent searches with the predictable efficiency. So this is the bar chart and line chart of AVL. So the recommendation, the part A is I think the AVL because it is a scalable and efficient data structure. It is a robust memory management and can handle edge cases. It uses the parallelization and partitioning for beta scalability. It can test and monitor for optimal performance and under maximum load. This is the instruction says the cons of the operation, AVL, BSD, and display. So this is a simple analysis of the AVL, BSD, and display. This is the most cons is in search. The AVL is as the number of insert nodes increase, both the number of operations and the rotation increase, but the growth of the rotation is slower. The total number of the movement is less than that of the BSD. In terms of the insertion operations, the AVL has more advantage than BSD trees. In BSD, in theory, the average number of moves for random insertion is close to the height of the tree, which is the big O log n. However, due to the possibility of imbalance in regular BSD, the actual number of moves will be higher than the AVL trees, so the value of the radio is less than 1. This is a delete the move counts. The AVL, the main factors affecting the number of moves includes the height of the tree. Higher tree require more rotation and the frequency of the rebalancing the tree after deleting nodes. The time complexity of a single deletion operation is a big O log n. The more time there are overall deletions, the more time there will be a linear increase in the number of moves. In BSD, as the number of the deletion increases, the number of the moves also increase accordingly. In BSD, the time complexity of deleting nodes ranges from big O log n and big O n depending on the balance of the tree. So the number of the movements in BSD is higher than the AVL trees. So there's a discussion for the instruction 7. Based on the question, my answer is the difference is the number 1 is the search and the insertion analysis. My analysis of trees emphasizes the additional overhead introduced by explicitly checking for duplicate keys during insertion, which increases the constant factor in the time on complexity while keeping it big O log n. This reflects the more practical implementation focused perspective. Radio science work focused on on-board tree balancing the mechanism across binary search tree, emphasizing the structural variance and its impact on operations. Its study does not appear to delve into implication level nuance like explicit duplicate checks. The second is the comparison matrix. My work details the impact of balanced maintenance, rotation, balancing factors on insertion and deletion times. Specifically, AVL tree maintains a balance with more rotation but exhibits lower comparison and move counts than the regular BSDs. Rudy's visualization provides a more conceptual understanding of imbalance effects on operation efficiency, focusing on higher level tree properties rather than the detailed metrics like move counts. The motivation for the further improvements is the first is the integration of conceptual and practical insights. Rudy's focus on tree structure and balance could inspire integrating high-level conceptual modeling into my experiment, particularly to test the theoretical explanation against the practical outcomes. The second one is the dynamic analysis with visualization. Rudy's use of interactive visualization highlights dynamic changes in tree structure during operations. This could inspire the development of similar tools to illustrate AVL tree balance maintenance during your experiments, making the results more accessible. The third one is the broader use cases. My analysis could incorporate more diverse datasets or operations to generalize finding further. Rudy's generic presentation of BST operations could guide exploring use cases beyond typical workloads, such as the highly skewed datasets. So the further work is the first one is develop a visualization tool similar to Rudy's but tutored for AVL BST comparisons, emphasizing balance factor adjustment, rotation counts, and their impacts on time complexity. Conduct experiments isolation system level impacts that catch behavior to refine practical insight into AVL and BST performance under real-life conditions. The third one is to explore hybrid approaches, such as combining AVL practice with characteristics with other balanced structure B trees for scenarios involving extremely high data volumes or parallelized operations. So that's all of my work to the system. Thank you.